In the video on atan2, I showed you a couple of examples of using this powerful built-in routine to rotate things any way we want. Let's look at one of those examples more closely here so that you can use the technique in your own code. The example I'm going to use is this one, where I draw these two animals with big googly eyes. I'm controlling the carrot with my mouse, and wherever I go, they watch. So let's take a look and see how this is implemented in code. I'll discuss how things work for the duck. The elephant works in exactly the same way. Once I've drawn the basic duck, I draw his googly eye on top. The first thing I do is I translate to the point where I want the center of the googly eye to be. Let's call that EX, EY for the point E, or the center of the eye. Once I've made this call, my coordinate system is now sitting right here. Notice it's a little bit behind the duck's real eye because I want to draw the googly eye very big. Now I'll draw a circle for the eye itself. I'll call ellipse. The center point is 0, 0 because I've translated to the point where I want the eye to be located. And let's say that the eye has radius ER for eye radius. Then when I call ellipse, I'll use 2 times ER for the eye diameter. Now let's think about the pupil. Where should that go? Let's focus just on the eye for a second. I'm going to draw the pupil on the positive x-axis. So the only question is, what is the x value for the center of the pupil? Well, let's take a closer look at the eye. And we know that the eye has a radius of ER. And let's say that the pupil has a radius of PR for pupil radius. I want to position the pupil so that the right edge of the pupil is just touching the right edge of the eyeball. So here's our coordinate system. We know that the distance from the center to the outside of the eyeball itself is ER. And we know the distance from the center of the pupil to the outside of the pupil is PR. So the distance I want to move from the center to position the pupil just right is simply the difference, ER minus PR. If I take out all of these construction lines, then here's the eye as I want to draw it. The value of drawing the eyeball on the x-axis is now I can call rotate before I draw the eyeball. Rotate, of course, rotates the whole coordinate system. So the eyeball just ends up wherever the x-axis is pointing. That's the technique we're going to use. So let's go back to the duck. We've already drawn the eye, and now I want to draw the pupil. So I just call ellipse again, where the center now is at ER minus PR in X, that's the value we just found, and the Y value is 0. And of course, the radius is PR, so the diameter is 2 times PR. I'm leaving out other stuff here like calls to fill to change the color, and push matrix and pop matrix, but you know that they're there. We're just focusing on the geometry here. So now let's think about how we're going to manage that rotation. Well, taking a look at the code, we know that before we draw the pupil, we're going to call rotate. And we're going to rotate by some angle, I angle. So let's see how to find that. Now looking at the duck again, remember, as I angle changes, we change where the x-axis is located, which changes where the duck is looking. So really, I angle is doing all the work. So how do we find this? Well, of course, we need to know where we want the duck to look. And in the example, I was having the duck follow the mouse. So here's the point that I want the duck to look at. Just to keep things short, I'll call the coordinates of this point MX, MY. It doesn't have to be the mouse, of course. It can be any point anywhere. But in my example, it is the mouse, so I'll continue to refer to it that way. Now we have all the information we need. We can draw a line from the middle of the eye to the mouse. And the X and Y values of that line can give us the angle that we're looking for. The X value is simply the mouse X minus the eye X. And the Y value is just the mouse Y minus the eye Y. Looking back at the code, just before rotate, we'll open things up and we'll call atan2. What are the arguments? Well, the first one is nothing more than mouse Y minus IY. And the second one is mouse X minus IX. That's the angle that we're after. So let's clear everything away and start over and see how this all comes together. First, we call translate to move the coordinate system to the center of where we want the eye to be located. and looking at the duck, there's the coordinate system. Now we call ellipse to actually draw the eye, and notice that the center of the eye is at 0, 0, because we've already moved where we want the center to be. Now, before we draw the pupil, we're going to rotate. By how much? Well, first we find the point we want to look at, and we find the differences between the location of the point we're looking at and the center of the eye. Using those differences, we call atan2. That gives us the angle. Now that we have the angle, we can call rotate using that angle. And looking back at the duck's eye, once we call rotate, the coordinate system rotates so that the x-axis is lined up exactly in the direction we want it to go. Now it's easy. We just draw the pupil on the x-axis. There it is, and if we get rid of the coordinate system, we see the duck is looking at the mouse point. So except for a lot of stuff you know about, like changing colors, this is the essence of the geometry for getting the duck to look anywhere we want it to look, and by extension, to get anything pointed in the direction you want it to be pointed in. There's an interesting subtlety with atan2 that I'd like you to know about. You may never have to care about this. It may never make a difference to you, but at some point it might. And to prevent you from going crazy, I want you to at least have it in the back of your head. Normally in processing, when we talk about circles and angles, we think of either 360 degrees or, as we saw in the video on angles, 2 pi radians going around the circle. They start at 3 o'clock, that's 0 radians, and going clockwise, the number of degrees or radians goes up. In radians, 6 o'clock is pi over 2, 9 o'clock is pi radians, 12 o'clock is 3 pi over 2, and by the time we make it all the way back around to 3 o'clock, we've gone through 2 pi radians. It's a little weird, but atan2 doesn't think of the circle this way. One way for us to think about it is that atan2 thinks that there's a top half of the circle and a bottom half. The bottom half is just like what we saw. Starting at 3 o'clock and going clockwise, we go through pi radians. But the top half of the circle, going counterclockwise, goes to minus pi over 2 and then minus pi. Now, the angles still go up as they go clockwise, but now we start at 9 o'clock with the value minus pi, and we go up as we go clockwise, and by the time we've added 2 pi to our starting angle, we're back at 9 o'clock where we started with a final angle of pi. So here are the two pictures side by side. On the left is the way we normally think about things, and on the right are the angles we get back from atan2. Now 99% of the time, you're just never going to care about this. You call atan2, you get back an angle, you rotate, and you go on. But every once in a while, you might write a program where you call atan2, get back the angle, and rather than using it right away, you do some math on it. Maybe you add something to it, maybe you subtract it from another angle. For one reason or another, you actually manipulate the number. If you do that and things look screwy, this is often the reason why. It's because you're thinking of your angles between 0 and 2 pi, and atan2 is giving you back numbers from minus pi to pi. As I said before, this may never become an issue for you, and if it does, it'll be because you're doing something really weird. So just squirrel this away in the back of your head and come back to it someday if you find yourself doing math with the values that come back from atan2 and things are going funny. But really, all you have to remember is that atan2 takes 2 arguments. And this is actually very important because there is a function called atan, and it takes just 1 argument, and you're probably never going to use it. Use atan2 with 2 arguments, the y value comes first, and then the x. And everyone messes this up from time to time because we always think of things in terms of x comma y. So if you're using atan2 and your angles are coming out all screwy, make sure that you are handing it first the differences in y's, then the differences in x's. Once you have that straightened out, you're going to find that atan2 is a wonderful routine that you're going to use all the time to draw really interesting geometry.